Hello, guys, and welcome back. Today, we'll be studying a very new and interesting topic, that is the dual nature of matter. That is continued in the part of the nuclear physics, or we can say the atomic physics. As discussed in the previous videos about the Young's double slit experiment, and also a bit of part of wave optics and the nuclear physics, I felt it was necessary that first you need to understand about the atomic physics. Then we can study more about the nuclear physics. And hence, today we'll be learning about the dual nature of radiation and matter. So, first things first, let us understand the modern physics. This is one of my favorite topics, if you see. And things in modern physics are dual nature of matter. The second one is the atomic structure, that is also called as atoms. Then the third one being nucleus. And the fourth one is semiconductors. So this is how the modern physics is developed. And in this today we'll be studying about this. And it is going to be a wonderful lecture. If you pay attention, we'll be going through some of wonderful concepts. Even Einstein's equation we will use here and there for some time. So should we begin or not? Let us first understand about the dual nature. What is actually the dual nature? So you might have studied about the dual nature of radiation, and that is radiation means light, and the dual nature of radiation is it travels like a wave, and in sometimes it also travels like a path of light, also known as a ray. And so it has a wave nature and also has a ray, also known as particle nature. This is interesting. And so we have proved now with the help of the string theory and many other interesting concepts that there exists dual nature of matter. And this is the thing that makes me wow. No, let that be. Let us make this teeth. Yeah. Like something like this would also go. Oh, yes. So there exists a dual nature of matter, and that's the OMG thing. So now we can say that a particular solid sphere acts like a wave and a particle at the same time. This is interesting. And so now we first come to the interesting experiment by Albert Einstein, which gave him the Nobel Prize. I think so, it was in the year 1916 or something that he got the Nobel Prize. And this paper, he released his research paper in the year 1905, which is considered to be the golden period of his life. So let us understand about the photoelectric effect. So the photoelectric effect in this experiment, there consists a particular glass tube which is structured somewhat like this. I'll draw it with the shapoifier. Shapoinator, that's a good word. Shapoinator. Whoa! This is just as stupid. I'll draw it by hand, that's the good thing. Yes, here and then somewhat like this. Just bear with me on my beautiful drawing without the help of Shapeoinator. And now here are metal strips of the same metal. There is this space. I'm making it large one for you to identify it easily that there's that space. And now let us go on modifying our circuit. So as for us to complete the circuit, there must be a battery which is obviously present over here. Oh, come on. So this is our battery, and we're not connecting the battery in such a bias. We're connecting it in such a bias. And to identify if there's a current going, so we use a galvanometer just for the detection of the current. So here's a plus, here's a minus. And now what we do? This part we see in this photoelectric experiment. This part being vacuum, and there is just metal present there. There's nothing present. Here only this metal rods are present, which I'll draw thick for you to understand. And now what we do? We bombard a light into it in such a way. I'll make it a bit like this. You'll understand why in a minute. So now I'm bombarding a light like this onto it into this manner. And then what happens is, what should ideally happen? If we do such an experiment, the light would slowly travel over here, and then at some point the electrons would eject out of it, and the electrons would move like this in this path, and they would go here, and the current would start flowing. So here's the plus, so here plus, here plus, here plus size, here plus plus. So it is a plus. Oh no. And if here there's a plus, so there should be a minus over here, because here plus minus for a potential battery V. So the electrons, these are the electrons. So electrons would move if the electric field is in this direction. Then the flow of current, this is, or charge we can say simply, that is the electrons will flow in the opposite direction of the electric field as they are negatively charged. So the current should flow after some time. But when we did the experiment, performed, what we should observe is like, after bombarding the light, initially the galvanometer is having no reading, it is at 0, and then when we bombard the light slowly, after a certain period of time the deflection should occur. But what actually happened was, when we bombarded the light from here, immediately there was a deflection. There wasn't a delay at all. Deflection of galvanometer. The scientists got curious, and the experiment was done by Albert Einstein first, and he was pretty curious. And so now he thought of an idea that maybe light is not traveling like a ray, it is maybe traveling like a wave. And a wave has a amplitude kind of sort of thing. And so if the light, even if we assume the light to be a ray, then the bombarded electrons, how can they reach so fast? And hence came the emergence of the photoelectric effect that we are going to study now. So, what Einstein did was he assumed a particle called as photon, which is known as packets of energy. And this packet of energy has a rest mass 0 and charge is neutral. Then its speed is c, that is the speed of light. It is an imaginary particle. Assumed, that means imaginary. And now what the Einstein's equation written is kinetic energy maximum of the electron is equal to energy provided by the for ejecting the photon minus the work function. This is the Nobel Prize winning equation of Herr Albert Einstein. And now let us understand what this kinetic energy max means. So now if we bombard with a specific energy over here, then the electrons would eject out with a kinetic energy equal to this. That is the kinetic, that is the energy provided minus the work function, and the work function is a particular constant of a metal. Yes, let me erase it. Yep. So now that you understood till this, let us understand one thing, that this E can be greater than or equal to 5 because kinetic energy cannot be negative. And yes, so now let us move further. Let us understand first of all, let us understand the de Broglie postulate. De Broglie said that the energy of a photon is equal to h into nu, and nu being the frequency, which can also be written as hc by lambda. As we can say, the velocity can be written as its frequency times lambda, that is equal to c for a photon, and substituting this into this equation, we get an equation that is E equals to hc by lambda, which is equals to h nu, and this is de Broglie's hypothesis, and it is still a hypothesis. It can be wrong, it can be right, but after experimentation we found out that this is true, but still we do not have a reason why particularly this h. And what is h? H is the Planck's constant. And the Planck's constant is a constant of obviously, and yes, we'll talk about it more. So de Broglie was doing his bachelor's and all those things, and during that he wrote a research paper in which he said that nature loves symmetry, and if nature loves symmetry, then if radiation is having two forms, then the matter should also have two forms, and that is number one as a wave form, and number two the particle form. And that is from where he gave this formula, which is from experimentation, and it is still a hypothesis. So there is no ultimate mathematical proof to this thing. So now let us discuss in Einstein's theory the threshold frequency. That is, the frequency is written by this and nu naught, threshold frequency. So what is the threshold frequency? minimum frequency of electron. So now E equals to h nu naught. So nu naught equals to C by lam. For minimum kinetic energy can be equal to 0 in our Einstein's equation, so which is equals to E minus phi. So E becomes equal to phi, while E is equals to h nu naught. So h nu naught equals to phi. So nu naught is equals to phi by h. This is the minimum frequency, that is the threshold frequency. Then the second term comes, that is the threshold wavelength. The maximum wavelength when kinetic energy is minimum. As we know, the frequency is inversely proportional to wavelength, and from this we write, if the frequency is minimum, then wavelength is maximum. So we can write nu naught from here as C by lam. So it becomes C by lam naught equals to mu naught. This is lam naught, which I am representing as this. So substituting it over here equals to h upon phi. Sorry, I wrote the equation now. Phi by h. So lam naught from here becomes ch by phi, that is hc by phi. The same thing after all. And this is it. We have got clear. Now let us discuss one more thing, that is the intensity. Increasing intensity in photoelectric effect. Increasing intensity in photoelectric effect. Now P does not stand for potential energy over here. Please keep that as a note. So intensity I is energy per unit area per unit time. And energy per unit time can be written as power per unit area. This is something that you might need here and there. So this is something to be kept in mind. So intensity we know now. So there are two ways of increasing intensity. That is the first one being the increasing energy of photons. So for example, here is a light bulb which is emitting photons that are of 3 joule. We'll write this in a different color, that makes it look more attractive. So here, yes, this is a light bulb giving out 3 joule energy of photons. And now to increase the intensity, we increase the energy, and now this particular bulb is now giving out photons of now energy save 5 joules. So now energy increased means intensity increased, but we are forgetting something. The energy of a photon is equals to hc by lam. So upon increasing the energy, there would be a decrease in the wavelength, that is color would change. And we have experimentally seen that the color does not change. So something is going wrong now. So what is going wrong? We are looking at the first thing, and the second thing being the increasing number of photons. This is a good thing if we say. Now, if there is this light bulb having 3 photons of energy, 3 joule, and now in order to increase the energy, I increase the number of photons to say 7, 4, 5, 6, and 7 that are of 3 joule. So now what we will write for intensity equals to energy per unit area per unit time. But what is this energy? This is total. So I'll write here E net. So now we can write it as Ne photon upon ET. That is number of photons into energy of one photon upon area divided by time. Yes, this is the correct thing. So please have a note of this because it is helpful here and there sometimes. I'll do have a note of it. And now the next thing to understand how photons are produced. So you might have studied something like this. I might not know, but still I'm trying to explain. Okay, so increasing this. And one more, that is in the center. Yes, this is our nucleus. Instead of this, I'll write it as plus 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 plus. And now there are electrons moving around it, and say the energy level over here is E2 and say the energy level here is E1. So we excite an electron from E1 to E2 first. This is the first step, is excitation. We give some energy by giving energy, and the second step is that it will lose that energy and come back to original energy level. And when it does lose its energy, then it gives the energy in the form of radiation. And that radiation is nothing but light. But now we have a formula for E, that is Hc by lamp. So this energy is depending on the lamp, that is the wavelength. So this is the energy. So if we say we have to calculate what the energy would be, so energy of a photon is h nu. So h nu is the energy difference, E2 minus E1. So nu equals to E2 minus E1 by h. There are basic questions upon this formula too, but you can derive it on the spot. Just the thing needed is the knowing value of Planck's constant h, that is 6.67 into 10 to the power minus 34. Yes, so let's move further. So now plotting graph of photoelectric effect Now let us first understand kinetic energy max equals to this E minus phi. So phi will be phi, and E, that is the energy given, is in the form of light, that is in the form of radiation, that is in the form of a wave, and that we can express in the form of photons energy, that is h nu minus, we can also write this phi in the form of h nu nod equals to kinetic energy max. So now here our constant, this is a c, this is a slope, and this is a y. So we can compare with y equals to mx plus c. So let me compare it quickly, mx c y. So if we now start drawing a graph, so here is our kinetic energy max. Oh, the graph would go a bit beyond, below actually. So I need to just make this, and then here is a kinetic energy, and this is our nu. So now that this resembles a straight line and its y-intercept is negative, so the graph would look something like this. Yes, absolutely correct graph. And this would be the work function, and the slope would be equal to h. And if we see this intercept, x intercept, where y becomes 0, so kinetic energy max becomes 0, so h nu nod is equals to h nu, and that is the condition for threshold frequency, that is nu nod, and that's there. So this is the graph. And yes, now let us discuss about the stopping potential. So now let us again go to our original image from where our experiment actually began, that is this. And now applying a potential. Now, yes, the original circuit consists of applying potential like this. But now we are starting to apply negative potential, that is connecting the battery in a reverse bias kind of thing. So what would happen now is that the, let this be here 0 and here V. Let the battery have a potential of V. So here V, here also V, here also V, here also V. So here it would have a potential of V, and over here let us assume as 0. So over here there's an increase in the negative charge over here, and so the quantity of minus charge would increase, and over here the plus charge would increase. So now the electrons that are coming from there, the photons that are coming from here, like this, what would happen to them? So now from here the electron is ejected out once again from our original story, from where we started. So it is ejected out over here with this velocity, but then it takes a U-turn and goes over here. But it takes time. because it is going with a velocity, so it decreases, the velocity decreases, then it stops. So now we are defining what a stopping potential is. It is the minimum potential needed to stop the fastest moving electron in the cathode ray tube. And we can also write it is in the textbook definition form, that on increasing the positive potential on anode, if you apply negative potential on the anode with respect to cathode, then the speed of electron starts decreasing, hence the photoelectric current will decrease. A limit will reach at which even the fastest moving electron will stop. This potential is called as the stopping potential. So let us quickly draw a graph of stopping potential. A graph of stopping potential and versus or V, that is a potential, and here is a I current. And now how would the graph look like? It would look something like this. And yes, now let's label these points. This is our stopping potential, while this is our saturation current. Now what is a saturation current? So saturation current is on increasing the positive potential on the anode. That is, if we connect the battery in the correct bias, forward bias. Now I am writing here for our saturation current. Now let us again draw that cathode ray tube in which our original experiment occurred, and now I am connecting it in a forward bias, that is V. So with the potential difference V, so here it would be V, over it would be V. So here the plus charge would accumulate, so I am drawing plus over here, and over here minus. So when electrons are fired from this side, this is an electron going with v velocity, so it would come over here. And now when all the electrons from this cathode would get ejected and the current would flow, then at that point the how much increase in the potential V you do, there won't be a change in the current, because the number of electrons would be constant, because the cathode ray has that many number of electrons, and if all the electrons are then flowing, then there won't be any further increase. So we can write it, upon slowly increasing the potential of battery, it will be equal to the rate at which electrons are released at that time. At such time the saturation current is reached. So now let us write these things mathematically. So for our saturation current, is the stopping potential is for our stopping potential, we first know that V, that is a potential, must be equal to work done per unit charge. So from here we can infer that W equals to VQ, and as it is an electron, so we write Q as E and V. So this is a work done, and kinetic energy max is equals to then EV. So we know that if we apply this much of kinetic energy, then it would stop. So this is the maximum kinetic energy an electron would reach after applying a potential of V. Yes, this is an important. And another thing that we have to discuss now is the momentum of mass of photon. We know that momentum P is equals to m into v, but for a photon mass is equal to 0. So P 0, no. So we restated the definition of momentum for a photon. So we wrote momentum as energy per unit velocity. And now this is derived from Einstein's equation, E equals mc square. So E equals to m square c square by m, as it was mc square. So I multiplied by m and divided by m. So it became m square up and m down. So m square c square is the potential, Em equals to P. And again the mass is coming. So this is just the definition. There's no such thing as a proof. And one more last thing is the Heisenberg's uncertainty principle. And that principle states that the error delta x into delta p should always be greater than equals to h square h upon 2 pi. So now what is delta h and delta p? Delta h is the error in the displacement and delta p is the error in the momentum, which will be always greater than h upon 2 pi, that is a constant. So this being said, this is an important thing once again. And along with this, we complete our first episode. We'll meet tomorrow and we will discuss about interesting part, that is Bohr's atomic model. That is a very important concept after this, and it would be much more fun. And in the third episode, we would discuss about the X-rays. Yes, and thank you for joining me. We will meet you soon in the next episode. Thank you.